So independence comes up a lot in probability, as you can imagine. In these kind of simple experiments, for example, where I throw a dice and I throw it again, the outcome of the first throw of the dice should not affect the outcome of the second throw of the dice. Okay, so those two events should be independent. Okay, so we can give a mathematical definition for that. Say events, event E and F are independent, okay, if the probability of E given F, okay, so given I know, say that my first sibling is a brother, this shouldn't affect the probability of the second sibling being a sister. So it should just be the same as the probability I anticipated if I didn't know anything about the first sibling. Okay? And of course this is assuming that the probability of F is greater than 0. Okay? Another way to write this, okay, an equivalent way to write this is to notice, okay, here this is equal to, tell you what, I'll move this down a second. This is equal to the probability of E and F given probability of F, okay, divided by the probability of F. So we could write this in a slightly more symmetric form, okay, that the probability of E, event E, and event F occurring is equal to the product of E times F. Okay, so notice I've just moved this probability of F up to the top and said that E and F are independent if the probability of E happening and the probability of F happening equals the probability of E happening times the probability of F happening. Okay, so that sort of makes sense. The probability that the first sibling, say, is a brother is a half, the probability of the second sibling being a sister is a half, so the probability of having a brother and then a sister is equal to 1/4. Okay? So what that's saying is, remember our conditional probability is saying that if I looked at the proportion of time that event F occurred, how often did E also occur? Well, it's just the proportion I expected in the first place. In other words, the fact that F has happened doesn't seem to have influenced the outcome of E occurring. Okay? So, informally, speaking, what this is saying is that knowing F has happened, so our event F, knowing event F has happened does not affect the probability of E, okay, occurring. Okay. Right. One thing to say as a warning, okay, So this is something that occurs quite a bit as a sort of so I'll even do this in red pen. Warning. Okay. Notice that when we talked about disjoint events, okay, that is the idea that E intersection F is equal to the empty set. So that means that there is no place, okay, where event E can occur and event F can occur. Okay. Remember, there's a rule for probability for that. That the probability of E or F is just equal to the probability of E occurring plus the probability of F occurring. Okay. All right. That is a different rule to the rule here, where I say E and F are independent. Okay, and that means that the probability of E and F is equal to the probability of E times the probability of F. Okay. Sometimes people get confused by these. They're two different concepts, okay, but somehow the expressions are somehow similar. This is sort of like, if I'm in the situation where the events are mutually exclusive, meaning that E can't happen and F at the same time, all right? So the things like, I can't have a brother as the first sibling and have the brother as a sister as the first sibling, okay? Well, that's equal just to the probability of having a sibling, which is just a half plus a half, okay? And that's different to the case of those two independent events, which is, say, where E is the event where the first sibling is a brother and the second sibling is a sister. Those are independent events, and there's a multiplication that happens. All right. So the assumption that I'm putting at the beginning of 1, this is saying that E and F cannot occur at the same time. This is saying, independence is saying, if E has occurred, it doesn't affect the chance of F occurring. Okay, it doesn't change the probabilities. Okay, independence leads to a multiplication of the probability of E and F. Okay, whereas two events being what we call mutually exclusive, okay, means that if we look at the union of those, we do addition. Okay, so there's two separate ideas. Try to understand the differences between them, because people often make this mistake, okay, when they're first learning probability. Okay, so mutually exclusive means both things can't happen together, okay, whereas in independence they can happen together. All right, E and F can certainly occur, it's just that the outcome of one doesn't affect the likelihood of the other. Okay, all right. So one thing that's great to show in that I usually show at this point, which I just do as a recommendation that you try, okay, is to watch the following video on YouTube, and I'll just get it up. I should just put it up on the screen over here. So there's this great video. If you search YouTube, Darren Brown, coin toss, okay, and there's this great video here from 2012 where Darren Brown essentially throws 10 coins in a row. So he basically takes a coin, throws it, gets a head, then throws it, gets another head, then throws it, gets another head, and gets 10 heads together in a row. Okay, and it kind of looks like a kind of cool magic trick, okay, but as he explains a little bit later on in his explanation video, really is exploiting a property of independence. Okay, so let's just investigate that for a minute. So if you're watching the video currently, please pause, watch the Darren Brown video, and then come back to my video, hopefully. But here we can show why this happens. So here's an example. What is the probability that a magician, or anyone really, gets 10 heads in a row? Okay. So we're saying, well, what's the probability that I throw a coin and I get heads, and then 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 heads. That's 10 heads in a row. Okay. Well, in principle, the first head that I get doesn't affect the second head, and the second head doesn't affect the third head, and so forth. Okay. So essentially the outcomes of the first coin, the second coin are independent, the outcome of the first coin, the third coin are independent. All of these outcomes are independent of one another. Okay, so I could say, well, the probability that the first head is independent of the probability of second head, so I can make that independent as a multiplication, is independent of the probability we get a head in the third coin, all the way up to that 10th head. Okay, and now the probability that I get heads on any given individual coin throw is a half. Okay, so I'm going to get a half times a half times a half, all the way up to the final 10th one. So we're going to get 1 over 2 to the power of 10. Okay, which you can check with your calculator is about 1 in 1024. Okay, so it's rare, it is a rare event to pick up a coin and throw it 10 times and get heads every time, but it's not sort of order of magnitude rare. Okay, so if we look at the if we just do the following calculation, how many minutes are there in the day? There are 24 times 60 minutes in a day, okay, which is 1,440 minutes. Okay, so let's suppose every experiment, okay, of throwing a coin 10 times took 1 minute. Probably takes less than that, but every experiment takes 1 minute. Okay, then, okay, there are a sufficient number of minutes in the day so that it seems reasonably likely that I'll have got one of these events to occur. Okay, so if I kept on throwing a coin 10 times and did it for a day or a couple of days, it seems quite likely, actually, given the number of minutes in a day, that I'll eventually get that. And as the explanation gives in the video, that's exactly what Darren Brown did. Okay, it took apparently about 9 hours or so, okay, given it takes less than a minute to do each one of these experiments, to get the outcome to occur. Okay, so this is why sometimes things, you know, the calculation rules that we use in probability are correct and get the right answers, but sometimes the orders of magnitude of things, or some of the outcomes that we get from the calculations, can be a bit unintuitive to people. Okay, and getting that kind of probabilistic intuition can sometimes be a bit difficult. Okay, so I mean, the kinds of things that people can sometimes get confused by, and it really depends on the person, is the idea of, you know, for example, that I say I've thrown a coin 99 times, okay, and I've got heads every single time, okay, then sometimes people wonder, well, what's the probability? People feel that after a big run of heads like that, you're kind of due to get a tails next, okay? But as we know, if they're independent, what's happened up until that point, even though I've thrown 99 heads in a row, okay, that doesn't affect the chance that the next coin throw is going to be a tails. Okay. All right. Next. So with our kind of conditional probabilities in place, there are a few rules that you can use for conditional probabilities. Okay. So let's just do a few rules for conditional probabilities. Okay. So just like normal probabilities, there are a few tips and tricks which are kind of useful to use. Okay. So first, that since the probability of B given A is defined to be the probability of A and B divided by the probability of A, okay, we can also note that the probability of A and B is equal to the probability of B given A times the probability of A. Alright? Okay. Now, this can sometimes be useful, and I'll give an example in a minute, but sometimes once we know that A is occurred, it's easier to calculate the probability of B. It's probably easier than calculating the probability of B on its own sometimes. Okay. This can also be combined with our previous probability rules. Okay, so note that since, for example, we take an event B, and note that B is the union of two disjoint events, one where A occurs and B occurs, or that A does not occur and B occurs. Okay, and so I can then say that the probability of B is equal to the probability of A and B plus the probability of A and not A and B. Okay, and then now I can use my rule up here. Okay, I can work out the probability of B as the probability of B given A times the probability of A plus the probability of B given A did not occur times the probability that A did not occur. Okay, that's sometimes a useful rule. So we've got one sort of useful probability rule here, another useful probability rule here, that the probability of B is equal to the probability of B given A times the probability of A plus the probability of B given not A times the probability of not A. Okay. A final rule that can sometimes be useful is that, well, the probability of B given A, okay, we know is equal to the probability of A and B divided by the probability of A. And now I could times and divide by the probability of B. Okay? So this is equal to the probability of A and B, okay, divided by the probability of B times the probability of B divided by the probability of A, okay, which is then equal to the probability of A given B times the probability of B divided by the probability of A. Okay? This gives me a new rule. The probability of B given A can be expressed in terms of the probability of A given B, as long as I appropriately readjust for the probability of B and the probability of A as follows. Okay? This is quite a useful formula. It's often called Bayes' formula or Bayes' rule. Okay, and Bayes is one of the fathers of a very popular branch of statistics called Bayesian statistics. Okay, so sort of roughly a good proportion of the kind of statistics that goes on these days is kind of Bayesian statistics. Okay, so now I'll quickly do an exercise here where we use some of these new conditional probability rules to do some calculations which are kind of similar to the calculations that we were doing previously, where we're using counting principles, and now we can see that we can actually sort of genuinely use these conditional probability ideas. Okay. All right, so here's the example. Okay, so the question is, what is the probability of getting 2 aces when 2 cards are drawn from a pack? Another question which I'll ask is, what is the probability the second card is an ace, ignoring the first card? So here we're going to ignore what happens with the first card and just ask, I'm going to take 2 cards out of a pack, I give you 1, 2 cards, what's the probability the second card that I give you is an ace? Okay, remember that if the first card is an ace, that slightly changes the probability that the second card is an ace. So ignoring the first card. Okay, so let's answer that question. Okay, so the previous way we would have gone about doing this question, just to remind you, is that, so I'll do this here. So the previous way would have been to gone that there are 52 choose 2 ways of taking 2 cards out of a deck. Okay, and out of those, okay, we count up the number of ways that we can get 2 aces out of a deck, which is 4 to choose 2. Okay, so the probability of an ace and an ace, okay, was going to be 4 choose 2 divided by 52 choose 2. Okay, which happens to be 6 over 1,326. Okay, right. So now we can do this with a slightly different method. Okay. So let's sort of let A1 be the event that the first card is an ace. We'll let A2 be the event that the second card is an ace. Okay. What we're asking for is the probability of the event A1 and A2. Okay. The probability of the first card is an ace and the second card is an ace. We know from our probability rules up here that this is equal to the probability of A2 given A1 times the probability of A1. Okay, so that's just one of our rules up here. Okay, this one. All right. Okay, and we can calculate both these terms, not too bad. So if I look at this one, well, it's just, there are 4 cards, okay, which are an ace out of 52, all right? Whereas for this guy here, well, given I've got an ace in my hand and I've got an unshuffled deck with 51 cards in front of me, there are 3 out of 51 chance that I choose an ace. Okay, so 3 possibilities out of a potential 51, okay? So it's 3 divided by 51 times 4 divided by 52, okay? Okay, which is going to give me exactly the same answer as before, okay? Alright, so that gives us a much quicker way. We're going to be dealing with not quite as big a numbers as we would with the counting methods. I find it's a much more intuitive way about thinking about how to calculate these sorts of probabilities, to think of things in terms of conditional probabilities. So sort of given the first card was an ace, well, what's the chance that the second card is going to be an ace? All right. Okay. So let's calculate the probability just on its own that the second card is an ace. Okay, so that was the second question that we had here. What's the probability the second card is an ace? All right. Well, I can use one of my other probability rules from up here. It's the probability of A and B plus the probability of A not and B. Okay, like this. So I can basically condition on what the first card might have done. That's what I'm going to do here. So this is equal to the probability that the second card is an ace, given that the first card is an ace, times the probability that the first card is an ace, okay, which I've just done the calculation for up here, plus the probability that the second card is an ace, given the first card is not an ace, times the probability that the first card is not an ace. Okay? And here we see that we've done the calculation for this, so it's 4 divided by 52 times 3 times 51, plus, okay, so what's the probability of not getting an ace? Well, there's 48 cards out of 52 where I can not get an ace. And then, what's the probability that the second card I get an ace? Okay, given the first wasn't. Well, there's 4 aces in the deck and 51 currently present after I've taken one out. Okay? And you can do the calculations on this guy. For example, we can notice that this is 4 divided by 52. Okay, taking out that 4 and that 52 and that 4 and that 52. 3 over 51 plus 48 over 51. Okay, which is then equal to 1. And 4 divided by 52 is just equal to 1 and 13, which is just the probability of getting an ace. Okay, so notice the probability of getting an ace on my second card is equal to the probability of getting an ace on my first card, which, if you thought about, you might well have thought about this question a little bit before I started to answer it, and it would make sense that the probability that the second card that I show you has a 1 in 13 chance of getting an ace, because think of it the following way. If I'd taken a card and placed it to you face down on the table, okay, or just put it back in the deck at random, well, put it back at the bottom of the deck, I've still got an unshuffled deck of cards here, and then I'm just showing you a card, okay? So maybe think of it this way. I'm going to give you 2 cards, one I put at the bottom of the deck and then give to you later, and then one from the top, okay? When I show you the card at the top, it's a 1 in 13 chance that it's an ace, and the one that was placed at the bottom I'm going to give to you now, okay? And that is still from a shuffled deck of cards, okay? All right.